In this section, we are going to study about how you can design an arithmetical and logical unit. We have already covered on how you can design an logical unit as well as an arithmetic unit separately. So in this section, we will be learning how you can combinedly design an ALU. Okay. So we already know that there are three selection variables that are being used, that is S2, S1 and S0. With these three selection variables, that is 2 raised to 3, 8 different operations can be produced. So with three selection variables, you can generate 8 different operations, and an input carry of CIN is also used. So if you use the CIN also as one of the selection variable, then additionally you can generate 4 more operations. With S2 is equal to 0 and selection variables S1 and S0, and together with CIN, so 3 selection variables S1, S0 and CIN, we can generate 8 arithmetic operations. That is 1, 2 and 3, 2 raised to 3, 8 arithmetic operations. And with S2 equal to 1 and selection variables just S1 and S0, 2 raised to 2, you can generate 4 logical operations or XOR, AND and NOT. So in this section, we are going to see how you can design an ALU combining these two circuits separately. Okay. So here in an ALU, each stage of an ALU consists of 6 inputs, namely AI, BI, CI, S2, S1 and S0. And there are 2 outputs that are being produced, function Fi and a carry out Ci plus 1. So the design procedure for an ALU basically has got 3 steps. First step is you can design an arithmetic section independent of a logical section, which we have covered in the class. And second method involves designing a logic operations which are obtained from an arithmetic circuit, assuming that the input carries to all stages are 0, which we saw in the previous video clip which I have uploaded. And the third method, you can modify the arithmetic circuit to obtain the required logic operations. So these 2 methods, 1 and 2, we have already studied. First method is using an arithmetic section alone, and in the second method, you're converting the carry to 1 and then making use of the arithmetic circuit to obtain the logical operations. And in the third method, you are modifying the arithmetic circuit to obtain logical operations. This third section will be discussed in the following video. Okay, to change the output of an OR operation, we have already seen in the previous video clip that we were able to generate only an XOR operation and a NOT operation in the logical operation circuit. So I've mentioned in that video slide that while designing an ALU, we'll see how you can actually generate an OR operation and an AND operation. So now we are going to see how an OR operation is being generated. So I hope you remember that table in which you have seen that the first instruction, I mean the first entry in the function table, when S2, S1 and S0 value is 1, 0, 0, then the operation that we got there is transfer, but actually we need an OR operation. So how you can convert this transfer operation to an OR operation? The only thing that can be done here is that transfer of A gives you AI. So if you are ORing a BI content to it, that is, you can add a BI content to it, then you can obtain BI plus AI, which will give you an OR operation. Similarly, we saw that instead of an AND operation, we got an equivalence operation in the previous function table of a design of a logic circuit. Now, how you can convert this equivalence function into an AND operation? What we require is this particular AND operation. How can we convert this? For that, you can use a Boolean function called Ki, and you can perform an OR operation with the content AI to obtain this AND operation. So Ki is performed an OR operation with AI. Now if you expand this, you get it as AI BI plus Ki BI plus AI dash Ki dash Bi dash. Now, if you are applying BI complement instead of this KI, you can rearrange this equation in this particular format where you are substituting every KI with BI complement. So here this KI is being substituted with BI complement. This KI dash is being substituted and given as BI. Now, if you reduce this particular equation where all the BI and BI dash gets converted to 0, so this term goes to 0, this term goes to 0, so the only remaining term is AI/BI, which is nothing but the AND operation. So this is how you converted an equivalence operation to an AND operation, and here an OR operation is obtained by just ORing a BI with the transfer of A, or just AI. If you are ORing BI, you get an OR operation in the case where S2, S1 and S0 is in the 1, 0, 0 value. And this is the case where you obtain an AND operation. So all the 4 logical operations are now being obtained in this particular circuit. So this is the logic diagram. Okay, so this is the logic diagram of an arithmetic logic unit. So this is how it looks like. So in this particular diagram, we actually shown 2 stages. So this stage is the duplication of this stage. So if you require n number of stages, you can just duplicate this stage. Okay, so as I've already mentioned, you have 6 inputs: Cin, S2, S1, S0, A1 and B1. Okay, and the outputs which you obtain is F and then C2, which is nothing but Fi and Ci plus 1. Now, from this logical circuit diagram, you can obtain the functions of Xi, Yi and Zi in terms of all the 6 inputs in this form. That is, Xi is equal to AI plus S2, S1 dash, S0 dash, Bi plus S2, S1, S0 dash, Bi dash. So coming back to the diagram, X is equal to, you're giving an OR operation. To that OR operation, which all are the content? The content is, first one is AI. AI is being given to this OR operation. So this AI is there. Okay. Then you have S2. Okay, you have S2, you have S1 dash, and you have S0 dash, and again you have BI. Okay, so that is S2, S1 dash, S0 dash and BI. Now you have another thing also, which is, okay, so which is, you have S0 here, you have BI here, you have BI dash here, and you have S1 here. Okay, so that is S2, S1, S0 dash and BI dash. So Xi you obtain in this particular format, and Yi, how you have obtained it? Yi you have directly obtained by S0 BI is ORed with S1 BI dash, and similarly Zi is obtained from which all components? Cin and S2 dash. Cin and S2 dash, you get Zi. Okay, now this is the general function for each stage of an ALU. Now if you give S2 is equal to 0, if you substitute S2 with 0 in this particular equation, when does an S2 equal to 0 is being given? This selection state S2 is equal to 0 is given for all the arithmetic functions. So when S2 is equal to 0, the respective equations Xi, Yi and Zi will reduce to this form. This is the 3 functions that gives the arithmetic function. Now, how do you get, or how do you convert the same logic circuit into logical circuit? By applying S2 is equal to 1. S2 is given as 1. When S2 is given as 1 respectively, this same equation get reduced in this format. So this 3 equations will give you all the logic functions. Okay. And this is the function table of the ALU, where a total of 12 operations can be shown or depicted in this circuit, with 8 arithmetic operations and 4 logical operations, 2 raised to 3, because 3 selection variables are used in this, and 2 raised to 2. 2 selection variables are used in this. So totally 12 operations can be shown through this diagram, one single circuit. So for exam, if it is asked to design an ALU, this is the diagram which you have to show, and along with the function table and each stage and arithmetic functions and logic functions need to be shown. So if they are asked only to design a logic circuit or only to design an arithmetic circuit, then the previous sessions will do, or the previous diagrams which we have seen will do. But if the question is to design an ALU, this is how you have to answer the question. Hope you have understood it. Thank you.